Everyone, today we are going to see about theorem 3.2. Let A be the infinitesimal generator of the analytic semigroup of t, then the function f belongs to L1 of 0 comma t of x, and assume that for every 0 less than t less than caps t there is a delta t, so that is greater than 0, and a continuous real valued function. The continuous real valued function is defined as wt of tau is up to 0 to infinity to 0 to infinity, such that we can define that mod of f norm of f of t minus f of s is less than or equal to that continuous real valued function, that is wt of mod of t minus s, and the integral of 0 to delta t wt of tau divided by tau d tau is less than finite. So the value is less than finite. Then for every x belongs to x, the mild solution of 3.1 is nothing but dut divided by dt equal to a into u of t plus f of t u of 0 equal to x. The to be continuous, our u of t will be t of x plus 0 to t of t minus s f of s ds. Okay, is a classical solution. Okay, for that we can take that A is an infinitesimal generator of the semigroup T of t. Let T of t be the analytic semigroup. We know that is the analytic semigroup. T of t is a solution, T of t of x is a solution of the homogeneous equation with the initial data x for each x belongs to x. We have to show that v of t equal to 0 to t minus s f of s ds, that belongs to d of a for 0 less than t less than t. So a v of t is here, a v of t is continuous on the interval 0 comma t. A v of t is continuous on the interval 0 comma t. So we write 0 to t t minus s f of s ds plus 0 to t minus s f of t minus 0 to t minus s f of t. For that 0 to t taken as common means t minus s f of s minus f of t ds dt plus 0 to t minus s f of s ds. So it taken this as v1 of t, this as v2 of t. Then from the theorem, what the theorem means, A is an infinitesimal generator of the semigroup C0 semigroup of t, then x belongs to x1 of 0 to t, x belongs to x, and 0 to t minus x dx belongs to d of a. Our a of 0 to t minus t x ds equal to t of x dx minus x. So for that we have v2 equal to 0 to t minus s f of s ds, that belongs to d of a, and our a of v2 equal to t of t. Here v2 is here x, here instead f of t. So t of t f of t minus f of t. Okay, then a v2 is equal to t of t take common, f of t take common means t of t minus I. Since f belongs to L1 of 0 comma t is to x, this implies that f is continuous on 0 comma t. So if it is continuous, f is continuous, then our a v of t is also continuous on 0 comma t. Then to prove some calculations of, we have to prove that a v1 also continuous. So we define, how we define means v1 of epsilon of t 0 to t minus epsilon t minus s f of s minus f of t ds for t greater than or equal to epsilon. So this one will become 0 when t less than epsilon. If t is less than epsilon means it will be 0. Okay, we have to prove the same calculation as that of v2, and we have to say that v1 of t of epsilon is equal to 0 for t less than epsilon. From this definition, it is clear that, it is obviously clear that v1 of epsilon of t tends to v1 of t as epsilon. If epsilon tends to infinity means it will goes to 0, that definitely v1 of t. It is clear that v1 of t belongs to d of a for t if v1 of 1 comma epsilon belongs to d of a for t greater than or equal to epsilon. A is applied to, here a is applied to v1 of epsilon for fixed epsilon greater than 0 and t greater than or equal to epsilon. A is applied to here, A is applied to v1 of t, and fixed epsilon greater than 0, t greater than or equal to epsilon. By using the theorem, A of v1 of epsilon of t 0 to t minus epsilon A into t minus s f of s minus f of t ds. Using the dominated convergence theorem, one can pass the limit epsilon tends to 0, we obtain dominant convergence theorem. We use a limit that epsilon tends to 0 to t a of t minus s f of s minus f of t ds, and by the closeness of a, to show that we have to show that v1 of t belongs to d of a. And here epsilon tends to 0 means it will be a v1 of t 0 to a of t minus s f of s ds, f of s minus f of t ds. To conclude the proof, we have to show that a v1 of t is continuous on 0 comma t for 0 less than t less than. We have to show that this one is continuous for 0 less than t less than t. We have a v1 of t can be written as 0 to delta delta to t. So 0 to delta a of t minus s f of s minus f of t ds. Here also is delta to a of t minus s f of s minus f of t delta ds. So for fixed delta, the second integral of the right hand side is a continuous function of t, while the first integral is o of delta, order of delta, that is also uniformly in t. So if it is continuous, this is also continuous. So a v1 of t is also continuous. Hence the proof is over. Hope you all understand, and thank you.